So I'm here to talk about neurosymbolic learning. Previously, like Ravi said, called statistical relational AI, and now the more popular version of this, people call it as neurosymbolic. Given that neural models are pretty much the statistical models, except the for people like us, statistical models give you a lot of guarantees that we don't get with neural models all the time. So there's a slight difference. But so what I'm going to be talking today actually is joint work with Ravi and his group. And really this was born, was it pre-COVID, right? When we talked about it in one of these visits, Ravi and I said, why not we just do this two-level system, like how humans would plan and act, right? So the plan for me is come and give a talk at IIT Madras, and I'm in Dallas. So what do I need? I just need a flight ticket. My parents are here. I'll figure out everything later. So book the flight ticket, give some dates. Then when you get closer to the date, you start figuring out other things. And then finally, when I'm taking the car from my house to the airport, when I'm booking the ticket, I don't think about what is the acceleration that I should be going at, what is the route that I should be taking, where should I park the car, how will I maximize or minimize the cost of parking. These problems don't occur when I'm doing the high level planning. We humans are very good at that. We humans can abstract out things as we need. So things that we plan early enough, and then things that you can just do in a reactive way or some sort of reinforcement learning agent taking over, that can be done. So Ravi and I were discussing this, if I remember correctly, during lunch one of the days, and then we put in a joint student, one from each lab, and then now we have this whole field of combining planning and deep reinforcement learning. So that's what I want to talk about. Have any of you heard about Daniel Kahneman? You have, right? Have you read the book? So which one? The Thinking Fast and Slow. Have you read the book? Yeah. So that's one of the really good non-fiction books I always recommend, right? And so if you look at the Thinking Fast and Slow, the idea with what we have here is kind of mirroring that idea. Okay, so we are all kind of inspired by the work of Daniel Kahneman to think about learning with multiple abstractions. So before I start, I really want to thank all my PhD students. We have Sahil here, who is going to be, by the way, co-teaching the workshop with me starting tomorrow all the way till Friday. So we have a very nice set of PhD students, and actually the most of what I'm going to talk about is the PhD work of one of the PhD students, Harsha Kokel. One second, I realize that the laser pointer is not going to work here. So Harsha Kokel's PhD thesis is what I'm summarizing, and of course all the key collaborators and funding agencies. But this particular talk, Harsha and currently I have Ranveer and Nikhilesh working on some multi-agent extensions of this problem, and Arjun was this really bright kid from IIT Madras who was working with us on this problem, I want to say about 4 years back, but it was pre-COVID, so maybe 5 years back. And then of course Ravi and my advisor Prasad, all of us worked together on this direction. The idea was when we started looking at this field of statistical relational learning, statistical relational AI, we wanted to really build systems that can learn and act seamlessly in noisy worlds. Where you have objects and relationship between objects. We are not talking of just pixel level information, right? We all have a symbolic idea of the world. I look at you guys, you all have a face, you all have a characteristics, you have some expressions that I'm figuring out whether you're interested in a topic or not. It's not just pixel level information that I'm working with. You're all objects, and then there are relationships between objects. People are sitting in the front, back, next to each other, and so on and so forth. And we learn to understand this world as a notion of objects and relations, right? So initially when we started looking at this field of statistical relational learning and AI, we were thinking of, okay, let's combine some sort of uncertainty modeling with logic, because first order logic can handle symbolic information very well, but then even graphs and tree structures and so on, and then we combined it with mining and data mining and learning. So we had a whole set of sub products fields emerging out of it, statistical relational learning, even association rule mining, and so on and so forth, things that were born out of this combination. And then of course in the last 10 years people were focusing a lot on scaling these to very large problems. But then slowly we realized that this whole community kind of grew around it, and that is the book that Ravi was referring to, Statistical Relational AI, where we said, well, this whole field can be then combined with satisfiability, knowledge representation, efficient search, data mining, computer vision, information retrieval, and so this whole field started forming around it. And then what happened was, historically this is how things evolved, and then what happened was this mining and learning really got replaced with deep learning. Right. So, the statistical side of things became neural, and then the symbolic models still exist. So, they are now more popularly known as neurosymbolic learning. There is a field called probabilistic programming. I think some of you would have heard of it, and even probabilistic programming kind of comes under this paradigm of problems. So, this is really the idea of statistical relational AI and learning, and I am giving you this a brief history lesson, if I may, so that you kind of understand the context of how the fields have evolved over time. Okay. Again, so when I'm when we talk of motivation of these problems, how are we solving these problems? The goal for me, for instance, is to I don't know. Just today morning, I decided I'm going to come give this talk. Well, all I'm going to figure out is I wanted to meet Ravi at some time. I had a meeting with Kamakoti at some time, so I have to come at this time. That's it, right? That's what I decide in the morning. Then when I actually sit on my motorbike, I figure out, okay, what is my easiest path to take? How much do I accelerate? Where should I wear my helmet? Where can I take it off? All these decisions are on the spot that I make. So in some sense, I have this high level plan which tells me this is the big problem that I want to solve, and then this is the decomposition of these problems that I could construct. Once I have that decomposition, maybe for each of those small sub problems, I can train a new reinforcement learning agent. So for instance, an RL agent could tell me how to get from, I live near Vijayanagar, or rather my parents live near Vijayanagar bus stand, Velachery. Okay, how do I get from there to IIT? Straightforward, but that planning is done by an RL agent. But once I come here, what do I do next? Again, a different RL agent will take care of that. So, so that's the idea, right? And so when I'm actually executing it, my reinforcement learning takes over, but I already plan and break it down into several possibilities. Think of writing a paper. Okay, you have different sections of a paper, but the key idea of the paper, it's born at a fairly high level. You talk to your advisor, an idea for a paper is born. Then what do? You break it down and say, okay, here are the hypotheses I have, and you design your experiments. You complete your experiments. But each of them at the lowest level is a reinforcement learning task. You start with something, you make some, let's say you're building an AI system, machine learning system, you run your experiments, see the results, get your feedback, improve it, keep going, and then now you go for your baselines. Of course, you have to carefully choose your baselines, because the baselines cannot be better than you. Nobody will accept your paper, right? I mean, that's unfortunately the sad state of academia today, but you cannot have a baseline which is equal to yours. It has to be worse than yours. So now you have to search for those baselines, right? And then you think about how you are doing it. But the fact is that each of these sections is a higher level task, and then each of these low level problems that you are going to solve is an RL problem. Make sense? And feel free to interrupt at any point, by the way. Yes. Mm-hmm. So, oh, absolutely. I mean, for now, the way I'm defining it, it's kind of top down. But the proposal that Ravi and I just got in to US Army was the one that says, well, we have to go back and refine them, because at each point you're assuming that you're creating the correct reinforcement learning instance. So for instance, let's say I tell you, I mean, we had this situation. Let's say that I want to book a ticket to IIT Palakkad, because Sahil's professor invited me, and now I figure out that this is the date I want to. I send the details in, but they say no, our university is closed today. We have a faculty meeting today. You get back, and then you realize that your constraints were not satisfied. So you have to redo your plan and send it back to the RL agent to do it. So absolutely, I mean, if you want this to be deployed in real time, I expect information to go both ways for sure. So what is the idea? Again, like you said, your name? Ahmed? Yeah, like Ahmed said, right, it's thinking fast and slow. there is one deliberative part which is very, it's in some sense it's slow, it takes its time, it reasons, but it actually has a very large understanding of the world. It has a very big picture of the world, which is your planner. It's very deliberative. It doesn't use quite a lot of data, but uses a lot of domain knowledge. Okay, it defines the tasks, you have some ontologies, you work with them, you construct it. But the most important thing is it is symbolic. So what it allows for you to do is generalize over multiple situations, multiple objects, multiple relationships between objects. Okay, then of course the problem with that is it doesn't handle noise and uncertainty of the world very well. It's a deterministic planner, so it kind of plans and tells you what to do. But it's most importantly, it's slow. It's not. It's by the name deliberative, right? It means it's pretty slow. On the other side, you have the reactive RL component. The reactive RL component, because it's again we know that it works very well. It can handle noise and uncertainty very well. But the biggest problem is generalization. You build a reinforcement learning task, how well do you generalize to unseen problems? Unseen domain really depends a lot on your representation, how much data do you give, and so on and so forth. What we are claiming in this line of work is that if I define appropriate decompositions of the problems into smaller subtasks that can be solved by RL agents, maybe you don't need lots of data. Maybe an RL agent can quickly figure out. So for instance, if I say from here go get some tea and come back, just to get to the door, you don't need that much trajectories. A few trajectories will teach me how to get to the door, and then from the door to the next whatever, right? So if you can break the problem into smaller subtasks, there's an efficient way of solving it. Ravi's I don't know, PhD thesis, what, 20 years back, 25 years back, was on some sort of abstractions, defining abstractions to accelerate RL. But what we are trying to do here is actually generalize it to larger problems and breaking down it into tasks and subtasks and so on. But you don't seem to agree. So idea for us is that we are combining high level planning with lower level reinforcement learning, right? Again, we are not the first to claim this. This is one of the requirement slides for my students to put our work in the context of existing literature, right? So there's enough work that talks about the combinations of planning plus reinforcement learning. Policy sketches is a classic example. You construct these modular policies, you break down the policies into smaller policies, so you can actually train each of them separately. Plan cue learning, again, it's a shaping function that allows the planner to shape the reward function so that you learn better. There's a POL, planning, execution, observation, RL framework, where the planner has a specific task where it is guiding the exploration. Okay, it's not doing anything but kind of telling you where to explore in the reinforcement learning world. And then there is another couple of systems. They are more on the robotic side to handle uncertainty in the in the state spaces. But the one that is very close to us is the idea of taskable RL, which formalizes the combination of a high level planner with a lower level reinforcement learning. The key difference between taskable reinforcement learning and our work is that we are in a symbolic space. So our planner is much more relational in the sense that you can talk of objects and relationship between objects. So if you think of a blocks world, you have blocks and blocks are on top of each other, blocks are on the table, and so on and so forth. Whereas taskable RL should say this blue block is on top of the red block is on top of the yellow block, and so on. So the identities of the block are important for taskable RL. In our case, the fact that they are blocks are all you need. So it allows for better generalization. Okay. Again, feel free to interrupt and ask me any question as we go on, right? So what can we do? One of the problems that many people acknowledge, one of the hardest problems inside AI and machine learning is the notion of relational reinforcement learning. Doing reinforcement learning in the presence of objects and relations. Think of real-time strategy game or any World of Warcraft or anything of that sort. You have these objects that are indistinguishable from each other, which means that if I replace object A with object B, they are the same thing. But I don't have to learn a policy that is specific to object A and object B. You can learn a policy that is for this particular type, right? Back in the day, what was it called? Strategus, Vargas. So you have these footmen. There are these real-time strategy games. You have footmen, you have archers, you have all these missile launchers, and for each of them you have a specific policy. It doesn't matter whether it is the green footman or the red footman. As long as they are your enemies, you kill them. it's very simple, right? And so you have to build policies that can generalize to these situations, okay? So what we combined was, our key contribution was, well, you have a planner at the top and you have a reinforcement learning at the bottom, not just one, several reinforcement learning, because what we do is we break down this high level task into smaller tasks, and each of them can run a reinforcement learning. But the key thing that we need in between is this layer of abstraction, because what does abstraction do? The planner will break it to a high level task. Let me give you an example, maybe concretely, right? And I'll skip this slide, right? So let's see. Yeah, let's do this as a concrete example. So I'll come back and talk about the rest of the stuff. Let's say that you are in a taxi world. Okay, this is I don't know if any of you were here in January. Tom Dietrich had come and he gave a great talk here on what LLMs can and cannot do, and he wrote this taxi domain in 1996. I think when he was in a sabbatical, right? So we can generalize it, and now you have this taxi. There are multiple taxis. Let's say there are multiple passengers who need to be picked up and dropped off in different destinations. Now let's just give a simple example. I want to transport both passengers P1 and P2. Now I'm going to break the task to say transport passenger P1. To transport passenger P1, I need to pick up the passenger and drop off the passenger. Same thing for transport passenger P2, and then I can do this pick and drop as their lower level sub action. So you need to get to that square, execute pick action, then get to that square, execute the drop action. Now if you look at this, right, this is the symbolic planner. It breaks the task down into smaller subtasks. At the lowest level, where you are talking about pick and drop, they can be done by reinforcement learning. I hope you can quickly see this, that this is pick, which means if I learn an oral policy here, I should be able to directly generalize it here. Same thing, if I figure out how to drop, and maybe if I break pick and drop to even go to this location, execute pick, go to this location, execute drop, then the go to oral agent can be used, just trained once, used 4 times. Okay, so that's the key idea for us. Okay, and so this can allow for generalization over different number of objects, and we can scale it to multiple passengers, multiple domains. Like Arvind pointed out, right, the current design is such that there is no feedback loop back up there. Okay, that's the next step for us. Currently in this framework, the RL agent is not telling the other person saying, hey, I can't go to that location is blocked, or there is a politician standing there, there's a rally going there, I don't know, I mean, so or if you are in Dallas, there is some flood there, right? So you just anything, right? So you can't give a feedback in the current way I am defining it, but that's what we are doing next. But what are the advantages? It's basically compositional, so we can decompose your tasks into subtasks. But the most important thing is, when I am creating this reinforcement learning agent at the bottom line, you are creating MDPs that are very small and that are very specific to that problem, so it's faster to solve each of them. Okay, but the most important thing is the thing in between, the abstraction reasoner. Okay, so if I am going to write this out, I don't think I have a whiteboard here. If I let me see if I have a slide here. No. Okay, so if I'm going to write this out, I'm not going to write it as transport P1 and P2. Instead, I'm going to say transport P, and this is an uppercase P, and then I'm going to say to do that I have to pick up passenger, drop the passenger, pick up this and drop this. Now if I say there are 2 passengers P1 and P2, suddenly that P, which is like, you know, think of it as a variable in Java, in C++, in Python, wherever, right? It's a variable that's going to be instantiated with a value. If the value is P1, then the location is different, but the value is P2, then it's a different location. Okay, P1 is in red location, P2 is in blue location. Now how do you know which one is what location? That is where this abstraction reasoner comes in. Okay, so I have a high level plan which is symbolic, and now with this symbolic plan I want to create a reinforcement learning agent, but somewhere in between is this high decomposition idea, abstraction idea, which decomposes your, which in some sense assigns values to your variables. Okay, and we also hypothesize, and we have shown some results on this side. This is where humans can be involved. You can put in a lot of domain knowledge, you can add domain knowledge to the problems that you have, and you can say this is task specific knowledge, this is subtask specific knowledge, and so on and so forth, that you can use to enhance your representation. This is very abstract at this point, I'll give you concrete examples. Yeah. Right. So the difference is that I think two differences. First is that the planner kind of plans it out for you and writes out it computes the plan. In a hierarchical RL, you have to completely define the hierarchy. Here, you just define the plan, and then the actual abstractions are instantiated by the planner. So you don't have to do the reasoning. So that's where the difference to hierarchical RL is. That's why I was pointing out to Ravi's thesis. That's, I mean, one of the ways of doing hierarchical RLs is that you can identify these groups and subgroups and so on and so forth. But in planning, it comes for free if you write the plan out. That's the advantage. The world? No, it takes as input the model of the world, but it can refine it. The more recent planners can do that. It's a good question. Excellent question. Thank you. Yes.
Go back to the previous
Example?
Yeah, example like so where do you draw the line between what has to be done
By the planner and where is the RL? Yeah.
For example, if I'll just try to if my two pickups are very close to each other, then maybe I can just do pick up one, drop 3.
Yeah. So the constraints will define it for you. So for instance, the constraints that we have in this domain is that there can be only one passenger in the taxi, but the constraints define it for you.
Correct. But it can also be something that we explore and find out.
Sure.
So where do you draw the line?
So currently the line is drawn by the application of the domain constraints. Okay, but you're right. In some sense, you can even figure out if you can learn those constraints, if you can adjust those constraints so that you can do faster learning. But the goal for me in this work is always to figure out that at this lowest level, I want to have as small as an MDP as possible, right? If I add another passenger to it, suddenly the state space becomes higher, the action space becomes higher. So you don't want to explode that way also. So currently, the way we are doing it is this abstraction reasoner kind of tells you where that MDP formation occurs. That's again a very good question. Okay, so what is the subtraction reasoner? It basically defines in some sense the notion of subtasks and when can you execute these subtasks. Let me give you a concrete example, right? So you have something like this. So you have these states, okay, so you have these green states and then if I do the black action, so these arrows are actions, okay. So if you have these shaded green shaded states, I don't know how to call them, and then you have these yellow or whatever gold colored states A, B, C, and now there are two kinds of actions. You can either do this green action or the black action, and doing one action will take from one state to another. Now let us say that the first task decomposition states that if you are in a green state and then if you do the green action, you will reach the state of the same type. That is the condition that I am putting in, okay, and then that will give you a reward of +1. Okay. Now if I define this abstract for just state 1, if I instantiate y with 1, x has to be only 2, because on executing the green action in 1 I can only go to 2. Does it make sense? So if in 2 if I execute it, I can go to 2 different states. I can go to 3 or to 5. Okay. So what this abstraction reasoner tells you is it defines how to instantiate the state values correctly. Okay. So if I do let us say 3, so what is the way I can get to 3? Well, there are two ways. I can either execute green in 2 or I can execute green in 3. So that is the task for, but that is on task 1, which is basically saying execute green from a green state to a green state. That is task 1. Okay. Now and then I can define the record and now if I modify that to say, well, there is also the possibility that I could execute black action from a green state, then I will go to a gold state. Now I can define for state 3, well, that means executing this could get me to B, but because 2 is also connected, 2 could get me to A. So you have these multiple options that you can construct, and you construct these smaller MDPs based on the problem at hand. This was the key insight of Ravi and I when we are doing this work on how to my planner at a high level says execute task 1, At reinforcement learning says, okay, now I have to learn for task 1, but it's at a high level. So this abstraction reasoner comes and says, for 3, this is all I need to know. All I need to know are A, B, 2 and 5, and that's it. This is all that is relevant for executing task 1. So now what do you have? You have the set of states, you have the set of actions. Your MDP will figure out how to do task 1. Make sense? And so what we can do is we can actually guarantee the abstraction guarantee. Again, right, this is from Lee and Walsh. We can say this is a model agnostic abstraction, and which means that no matter what your models are, we can actually guarantee that this is a safe abstraction. Okay, again goes back to Ravi's thesis and others' work as well back in the day. Okay. Again, there is a lot of problems that we are still working on, and this is an open invitation because I know Ravi is also looking for somebody to work on this, and I am looking for a couple of people to join us. So we need several ideas. First is, what if the observations are not complete? What if it's only a partial observation? So the underlying MDP, is a POMDP, for instance. How can you solve it? And then the idea for us is, okay, maybe we can use some sort of, and this probably goes back to Arvind's question, can we use some sort of reasoning systems in a probabilistic way, sound probabilistic semantics that passes the information from top to bottom, but also goes back up, right? And again, there's some work in this direction, and I'm going to kind of skip this because these are, I have not introduced these topics, but there's a lot of work here that we can do. And of course, I am calling it the dream REPRAL because Arvind, this is exactly what you asked me in the first part. It's a dream. Sorry? Dream. That's a good one. Okay. This is a dream REPRAL, which is my dream. How can we solve this? We want deep reinforcement learning agents giving feedback back to the abstraction reasoner. Hey, you defined a state space. This state space is not correct. It's not enough. You gave me an action. I can't even execute this action. You gave me a reward function. This reward function is completely wrong. How do you learn this? How can you give it back to the system? And I think this is where Sahil's tutorial tomorrow or day after, I think, is very important, because we can represent these using probabilistic circuits. Then these are differentiable, and then we can give it back up to this. So this is the proposal that got funded for Ravi and I, and we are hoping that we'll recruit some students to work on this. Okay, so again, I just want to give a couple more examples. So for instance, if the taxi is a location L, and then if the direction of the taxi moves in a particular direction, then it comes to this location L2. And you can define how L2 and L1 are defined. And for a passenger pickup, to pick up a passenger, taxi has to be in that location, passenger has to be in a different location, and the passenger has to be in that taxi. That's when you say that the pickup action has been completed. So you can define these kinds of abstractions correctly. Once you write this out, you can execute it, and then we can figure out how to solve this. So the idea is, it's a continuous loop. You have a high level plan. For each sub goal, you loop until the sub goal is achieved, get the abstract state, execute the policy, and then update the policy and keep continuing until you converge. Okay. So as examples, right, so we had this experiment on the taxi domain that I talked about. There is also this coffee world where you can bring coffee from one place to, somebody wants coffee, you go to the kitchen, get the coffee, deliver it to them, or go mail, deliver it to them. Then there are multiple coffee locations, multiple mail locations, and then there are this relational box world where you have to gather a key and open something, the box of that color, and it's kind of built on an Atari game, I think, but with multiple keys and multiple boxes and relationship between them. And here again, you can you can cut wood, bring it to the workbench, you mine iron, bring it to the tool shed, get gold, bring it to the factory. So it's inspired by the by all these real-time strategy games. Okay, and we compare against the other framework, and the most important thing that I want to show is this is REPRAL, which is our work. It's of course sample efficient because it's defining smaller abstraction, but the most important thing that for me is very cool is that you learn once, you get generalization for free. So if I learn how to transport passenger P1, I basically can transport any number of passengers. I don't have to relearn. Whereas the lower level things that don't allow for generalization, don't use symbolic representations, have to relearn that multiple times, right? And in office world, if I can learn for deliver mail, deliver coffee, now if somebody wants both or some of them, you can easily transfer. It's for free. So this red line means there is really zero shot generalization here, okay? And same thing with craft world, with transfer you can get faster. So you basically say get wood and iron, now you have to make stick. To get that you have to get wood, you have to get iron, and then you can make a stick. Again, it's done for free, whereas other methods need to be learning them from scratch. And of course we can also collect keys and open logs. You can collect multiple keys, multiple logs, and so on and so forth. And then obvious question is, well, how is the representation here? The underlying MDP was still discrete. So then we said, how about we just use images? The idea was very simple. We just said we can get the taxi location, geography, and current location from the image, and then you can get the unstructured image of the taxi. So essentially what we are doing is you have an image preprocessor here just as an input. We combine the two of them, some discrete representation with images, and essentially done deep reinforcement learning at the leaves. So we just learn directly from the images, and here actually we compare against for instance deep Q learning, DQN, and as you can see for one passenger not much difference, but then if I go for multiple passengers all the other things fail, whereas the REPREL that we have is very cool in the efficiency. Same thing with transfer, we get zero shot generalization that other methods kind of struggle with. Again 2 passengers, 3 passengers, and so on. There is a lot of work in this direction, I think particularly in the last 3 to 4 years, and I think we should be leveraging some of these, which is should we learn these high level planner also from data, maybe that goes back to how can we refine the planner based on the reinforcement learning, modify the plan based on the RL capabilities, and I know that task and motion planning inside robotics, for instance, people have been doing this for a while. How can we use that as well? So there is a lot of work in this direction that we can be inspired by and do this. And very recently we have been looking at multi-agent systems and thinking about the planner as some sort of a centralized controller. So the goal of the planner is not just to decompose anymore, but also identify who is fit for the job, right? So I am not going to ask everybody to do everything. I decompose it into subtasks, but every task is assigned to a particular learning agent. And so again this is exactly the same as the previous case, except now we are also going for reinforcement learning that learns task specific policies. And here we use the idea of goal directed relational Markov games. This is a work by Michael Littman nearly 30 years back, and we modeled exactly using this, and it's, if you look at this, the model is the same. You have a higher level hierarchical planner, but the planner also figures out which agent guesses which task, and then our abstraction reasoner then exactly tells what is the MDP for each of them. Here are the caveats: the agents don't communicate with each other, and that is important. So this is a very initial work in this direction. Let's say that one agent gets the box to the door, the next agent has to pick up from the door and go out, but the second agent has to keep the door open for the first first agent to give the box. In our current formulation, that is not done. We just assume that the box somehow goes there and it magically transfers to the other person, right? So, but we humans, we have a visual cue. I can look at your eyes and I know what you are thinking. You can look at my eyes and we have this thing, right? So that we don't collide into each other. We avoid that somehow. Most people, not everyone, but most people, right? And we can understand this. How can we get that communication between agents when in our work we don't do that? So that's a very important caveat of our work. Again, in taxis we have now multiple taxis, multiple passengers. You have to avoid collision, right? You can't collide at the same time. You don't want to go to the same passenger at the same time. So the controller kind of figures out who's most optimized in picking up which passenger and dropping off where. So that's decision taken by the controller, but the RL agents then continue dropping them. So again, if you see this, it's the same idea, except we assign a specific agent during the decomposition function. right? And again, obviously good results. Otherwise, I'm not I'm not going to be talking about that. And basically, we can actually exploit these symmetries to very large extent. It really works well. So what can we do? The goal for us is somehow have a differentiable planner, differentiable reasoner, differentiable RL, so we can communicate both top down and bottom up and learn in both ways. We are using one of the things that we are trying to do is see if we can use LLMs to kind of provide a jump start. So for instance, Rao Kambambati's group has always established that LLMs cannot plan, but on the other hand, LLMs can do shallow planning. They can do one step plan very well. So can we just use that, maybe approximate these plans instead of using a full planner, use the correct LLMs to get that one shot plan and then instantiate an RL agent based on that one shot plan. Maybe LLMs can actually do your abstractions as well. And so we are trying to do all that on this side. Of course, our bigger challenges are we need GPUs all the time, and we can't beat people in Google, for instance, ever on any of these problems. Okay, that's what I'm trying to do. So again, if you think about what we did, we want to go first think of good foundation in different types of foundation models, good models that are efficient and generalizable, like the reinforcement learning models that are very good, but then allow for rich human inputs, in this case abstraction knowledge, and then finally close the loop, somehow go from learning what you can at the lowest level and propagating it back to the higher levels, right? Again, I'm going to skip all this, but I do want to talk about one of our work that I'm really interested in, which is this idea of using human knowledge even during planning. So one of the recent work in this direction that we did was, if I give you some sort of knowledge, domain knowledge, can the system say, okay, I'm going to ask you the right questions when I want to, right? So you think of building an agent. The agent is going to say, okay, I'm going to figure out how to do the planning, but then I'm getting stuck at some point, or I have an uncertainty over the plans. Then I'm going to figure out what is the right question to ask. So again, I use this as all the time an example. I have an 8-year-old kid. When COVID hit, he was about 4 years old, and we started building Legos, and I was the guy, right? So I give me that Lego, give me this Lego, and then I kept building it for him. Around 1 year into the COVID, suddenly he said, one day he just came to me and he said, "Appa, shh, you keep quiet. I'm going to build. I will ask you when I have a question." So that's my aha moment, because the kid now knows what he knows, but most importantly knows what he does not know and can ask that question. Now how can we make that in a reasoning system? How can we have a reasoning system to ask that question, what does it know, and when can it ask the question about what it does not know? For some models, like like if I'm using a probabilistic model, right, Bayesian network, you can compute uncertainty. You can basically learn some sort of a distribution, and then you can compute marginalize out at that distribution, and if you want to learn more about it, please come to the tutorial, but you can marginalize out, and then you can say, okay, I have a high uncertainty in this region, so I'm going to ask you a question. But how about in plan? A simple idea that we did was, we had simulators, like internal simulators, not external simulators, but internal simulators. I'm going to say, how many of you have watched this Sherlock Holmes movie, the one starring what is his name? Robert Downey Jr., right? There, this repeated pattern comes. He closes his eyes, does a planning. I'm going to do this, and then that counter punch is coming like this, then I'm going to punch, do that, this. That to me is a rollout. Basically, this is, I'm closing my eyes, I'm imagining how things are going to happen. I mean, chess players can do that apparently really well, right? And so what we thought was, when I'm doing these multiple rollouts, can I figure out where I will fail, and then ask a question there, okay? And turns out that we can do that very well, and what we showed was, if we give you these preferences where the human gives knowledge before learning, you get this blue curve, which is the number of problems that you can solve, okay? It's pretty good, right? But then when the system can ask questions, turns out that even with like 10 questions, or actually in this case 7 questions, it can reach optimal performance. You can actually solve way more problems. Same thing with Block's world. By the way, AI is now what, 70 years old, we still haven't solved Block's world. Okay, it's one of the toughest problems to solve, and we still haven't solved them. And I mean, this is a restricted Block's world, even though I show 100% problem solving. It's a very restricted Block's world that we have worked with, okay, and free cell and so on. And this is pre-LLM era. So we have to now combine this with LLMs, but we actually worked with Professor Martha Palmer, Dan Roth, Julia Hackenmeyer, all NLP experts, on actually building interfaces where you can take input in natural language, domain constraints in natural language, and then somehow combine that into a formal first order logic representation, and then use that as constraints in your planner. So whatever questions that the system asks, system will ask a question, will reason in logic, but will convert that question into English and then ask it to the human. And we did some human experiments based on this, and very interesting questions. I was going to give some examples, but for instance, if you want to build an L shape, and the L shape was built like this, the system is going to say, well, I built this, but now you tell me, should the width be the same as the height? And so it's trying to figure out the geometries. And then I think maybe I'll give you an example, right? So I wanted to do this. So I'll say first build an L shape, then build a T shape, and then build this shape. So it's going to ask questions specific to those shapes. Is it always the case that the height is one more than the width? And then the person is going to say no, it's independent of those two. So then it says, okay, so now I have to parameterize them. So it kind of learns when to generalize and when to specialize the models that it has learned. Okay, so that's where I think my 50 minutes are up. So what we are really interested is in the combination of planning and reinforcement learning, and we think that an efficient abstraction reasoner is important, and this combines idea from planning, reinforcement learning, and statistical relational AI. And of course, the way we think about all these problems is that there's a presence of domain experts, and we can talk to these domain experts, treat them as an ally, and AI system somehow needs to efficiently use this domain knowledge and input, right? And it's important to get lower level feedback and update the planner and reasoner, and this is again ideas from age old theory refinement, and when I say age old, it's 1980s, 1970s. There's a lot of work on first order logic and theory refinement that I think are valuable right now, even in the era of LLMs. Okay, that we are going to go back to those ideas, and I think this will allow for efficient and effective generalization. And to me, it's extremely important to make systems that knows what it knows, but most importantly does not know when to knows when it does not know. Okay, that's where I think that's a real problem, right? Sahil will show an example, I think tomorrow. He was asking this probabilistic query, and the probability answer came out as 1.05. Okay, so if you don't know the answer, you better keep quiet, right? So how do we make those systems do this right? So with that, I can take more questions. Thank you.